Alright, hello everyone. Sorry for the quick break. Any questions about what we've covered so far? Any questions about the binomial distribution or discrete random variables in general? I'm happy to answer those in office hours as well this week, Tuesdays and Wednesdays 1 to 4 p.m., or via email, or at the start of class next time if you have any. And so if you're watching by delayed viewing, make sure to email me with any of those questions, and I'll answer them whenever I'm able to. All right, so let's quickly jump then into our last distribution type for the day. And so this distribution is called a Poisson distribution. And for a Poisson distribution, what we're envisioning is there's a fixed length of time, and we're counting how often something happens in that length of time, given an average number that we expect. Okay? So a simple example, I have examples down here. If I'm trying to manage foot traffic and staffing levels at an emergency room, I might need to know how many patients do I expect to arrive between noon and 1 p.m. on a given day. Now obviously each day may be different, no idea what might have happened that day versus another day, but if I have an average and I have enough of these other conditions that are satisfied, I can use a Poisson distribution to estimate that. Okay? Another example, if I'm in product manufacturing, I'm perhaps in quality control, and I want to know, I'm shipping out 100,000 of these products, how many of them are going to be defective? Well, the number of defective products in a given shipment is going to vary from one shipment to the next because it's a random process. Nobody intentionally puts in the defective product, at least I hope. But if I know the average number, I can use the Poisson distribution to model the likelihood of a certain number occurring. Okay? So the things to look for to know if a Poisson distribution might apply. Each of the events that we are counting need to be able to occur independently and can occur at any time in the interval, right? There's no 5-minute window during which time patients can't come in. And there's no collection of products in that shipment that are guaranteed not to be defective. The average rate doesn't change over time. We do need that average to be consistent for this idea to work. If it's not, then we'd have to use a more continuous distribution. And there are distribution types that do that, but we won't see them in this class. And then the last thing, this is most interesting, the probability of an event occurring is proportional to the length of time. In that sense, what it means is if I ask what's the probability I will see at least 5 patients in this hour, well, that might be a certain probability. If I ask the probability for seeing at least 5 patients in the next 2 hours, it should be proportional, right? Or excuse me, at least 10 patients in the next 2 hours should be almost the same. That's what we want here. We want this to scale up across intervals in a proportional way. All right. As long as those 3 things are true, then we can use a Poisson distribution. And the way we will denote a Poisson distribution, similar to the binomial, rather than a B for binomial, we'll use a P for Poisson, and I'm going to use this script P. So I would say that the random variable x is distributed like a Poisson distribution with parameter lambda. And this lambda is the average rate that I'm expecting. So if I know the average number of patients that arrive in an hour, that would be the lambda that I report here. This is a 1-parameter distribution. I needed 2 parameters for the binomial. I needed the number of trials and the success rate. Here I just need 1. I need the average number in that interval. So this is how we denote it. And what kinds of things can we do? Well, just like with the binomial distribution, we want to find a formula for computing specific probabilities, the probability of a certain number of those events. And we want to know the expected value and the variance. The first of those is unfortunately not easy, but again, Wagner's calculator will help you with those calculations. I'll show you the formula, and we will do an example. So for a Poisson distributed random variable, if the parameter is lambda, the probability that I see a specific value little x here is given by e to the minus lambda times lambda to the x over x factorial. Now that's a lot of different math functions all in one. I have an exponential here, whatever my average number expected is, I'm raising it to the number I'm looking to see. X factorial is that same factorial we saw in the binomial formula a few minutes ago. And this e to the minus lambda, if you've seen this e before, great, hopefully you recognize it. If you haven't, it's a specific constant in mathematics. It's 2.71828, 182.845, 9045, and keeps going. It never repeats, never terminates, but it's a very important number, kind of like pi. It has a specific name, just e. It's the natural exponential number, and it's called that because it comes up in an incredibly surprising number of places with very, very important applications. I can't possibly describe all of them here for you, but I just wanted to warn you, it's really important. So when you see e, it has a name for a reason. It's really a big number. Your calculator probably has an e button. And that's what you should use because it will give you more decimal places than, say, 2.718 would give you. All right, so just to make sure we know how this formula plays out, let's look at this one example here. If I know that the historical average number of patients arriving in the lunch hour, or in the after lunch hour, is 5, okay, I'm just throwing a number out there so we can see what happens. On a given day, what is the probability that the number of patients is exactly 4? So in that same hour, on some other day, I'm asking what's the probability I see exactly 4 patients today, when on average I see 5? That's a reasonable question, right? If I could understand that pretty well, then I would know what staffing levels I would need to cover almost all situations. And of course, I could have people on call to help for those extremely rare situations where there's a large number. Okay, well, how do I do it? I'm asking for the probability of exactly 4, so that's my little x. And on average, I see 5, so that's my lambda. That's what this letter is. It's the Greek letter lambda. So I have a Poisson distribution that is distributed with lambda being 5, and I'm asking for the probability. I'm asking for the probability that it equals 4. Alright, so what's my formula? Let me write this down real quick. So the probability it equals little x is e to the minus lambda times lambda to the x over x factorial. Alright, well, I see 5 patients on average in the after lunch hour. I want to know the probability of seeing exactly 4 of them. So that's going to be e to the minus 5 times 5 to the 4th over 4 factorial. Alright, so you can type all this into your calculator. It's not a fun calculation, but your calculator will do it. And it looks like there's about a 17.5% chance that I'll see exactly 4 patients if the average is 5. And it's Poisson distributed. Okay. What if I did another example here, where I have a manufacturer and they manufacture bolts. 1.5% of their bolts are defective on average. If I have a box of 100, what is the probability that exactly 2 are defective? I'll use y in this case. How would I do that? Well, I first need to think about, is this Poisson distributed or not? I'm counting the number of defective bolts in a box of 100. If I had 2 boxes of 100, I would think that that average would double. If I had 10 boxes of 100, I would think that average would multiply by 10, so it does seem like it scales in that same way. Any number between 0 and 100 could be defective. So I think that that does fit all the conditions for a Poisson distribution. And the parameter would be the average I would expect out of 100. What would that be? What average would I expect out of 100 to be defective? Well, it's 1.5%, and so out of 100, that would be exactly 1.5 of them. So that's the parameter I'm going to use. Now I'm going to use the same formula. E to the minus lambda. So here that's e to the minus 1.5 times lambda to the variable value, 1.5 to the second, over the variable value factorial. And if you compute that, it's about 0.25102, 25% chance that I'll see exactly 2 defective volts out of 100. What's the probability I see none? That means not one of the 100 volts is actually defective. Same idea, just plugging in 0 for my variable value. So e to the minus lambda times lambda to the variable value over the variable value factorial. If I raise something to the 0th power, I get 1. 0 factorial is also 1. 1 over 1 is 1, and multiplying by 1 does nothing. So all of this is irrelevant. It's just e to the minus 1.5. And what is that? That's where I definitely have to use the calculator. 22.313%. All right, well, one more question on that. What's the probability that no more than 2 are defective? So that's a way to write that mathematically. If I want no more than 2 volts to be defective, that means I want my defective count to be at most 2. Could be 0, could be 1, could be 2. And in fact, that's the way we calculate it. We take the probability equals 0, add to that the probability equals 1, and add to that the probability equals 2. And those 3 cases together cover everything. Well, luckily for me, the case where y equals 2 and the case where y equals 0, I've already done. So all I need to add to that is the case where y equals 1. And I'll just go ahead and write down what these come out to. This was the 0 that we calculated already. The 1 we have not calculated, I'll leave it to you to do so, using those formulas or using Wagnar's calculator, which I'll show you how to do in a moment. Okay, and this was also the one we calculated a minute ago. When I add those things together, the probability of at most 2 defective volts is actually pretty good. 80%, almost 81%. So those are the chances that I'll see 0, 1, or 2 defective volts out of 100 with a 1.5% defective rate. Okay. Well, so let's switch back to the slides then. And if I want to know, given a Poisson distribution, what the expected value might be, let's think back to that example a moment ago with the volts. The defective rate, the thing we used for lambda, was 1.5. Out of 100 volts, how many would we expect on average to be defective? 1.5. It's the same reasoning. And in fact, this alpha, or excuse me, this lambda, it is our long-run expected average. It's always going to be equal to the expected value. Okay? So the expected value for a Poisson distribution is lambda. Interestingly, and this takes a little work to show, but it does work out this way, the variance is also lambda. So once you know that one parameter, you can simply write it down as the expected value in the variance. There's no calculation required. And then from that, of course, the standard deviation is the square root of lambda. Now, in practice, I don't want to do a lot of these by hand. I can do it. I can type it into the calculator to calculate the exact values. But it's a lot easier if I have a calculator to help me with this. And again, Bognar steps into the rescue. So let's click and see what he does here. And I'll zoom in a little bit more so you can see it. Let's do the example we were just looking at. All right, I expected 1.5 of my 100 volts to be defective out of 100. And I wanted to compute the probability that exactly 2 were defective. That was my first problem. Well, there it is, 0.25102. That's the number we found, in fact. We then looked at the probability of 0. There's that number, 0.22313. And then we looked at the probability that it is less than or equal to 2. I think we found 80.885%. And sure enough, there it is. It covers these three cases: 0 defective volts, 1 defective volt, or 2 defective volts. And that's a total of 80% in all cases. If I wanted to know the probability of at most 4, that's 98.14%. Almost all the time, I'll have 4 or less defective volts. You'll notice, here's the expected value written out for me. Here's the variance written out for me. These things will always be the same for a Poisson distribution. And the standard deviation is the square root of the variance. So square root of lambda, whatever that happens to be. What if I was looking at that situation with patients in the ER in the after lunch hour? All right, so here's that situation. These are the probabilities of individual counts for the numbers of patients. Obviously, I could see 12, even if the average is 5. I could see 100, technically, but it should be a pretty rare event, and you'll find that the probabilities go to 0 as it tails off here. On average, I expect 5. My variance is 5. My standard deviation is a little bit more than 2, almost 2 1/4. What's the probability I see at most 5 patients? 61%, 61.6%. What's the probability I see at least 5 patients? 55.95%. And what's the probability, if I wanted to find the probability I see between 5 and 7, what I could do is I could take this number, which is 0.55951, and subtract this number, because these will be the ones I don't want. And that would leave only the 5, 6, and 7 cases. Or I could simply look at 5, 6, and 7 separately and add them together. Whatever's easiest for you. Just be aware sometimes there's too many cases to do it that way. So that would give me, 13% less than the 55.9, 42.6%. Should be the probability of seeing 5, 6, or 7. 5, 6, or 7. Should be about 42.6%. All right, questions about that? I think that's most of what I have. All right, so let's do one more example. And let's use Bognar's calculator to find this. And so this is actually a real biological situation. The number of eggs that a female grunge beetle lays in her nest has a Poisson with parameter 4 distribution. Find the probability that a given nest has at least 3 eggs. So that would be the probability of 3 eggs or 4 eggs, or 5 eggs, or 6 eggs, or 7 eggs, or 8 eggs, and so on. Right? If I was doing that on pencil and paper, that would be really tedious, and I'd have to keep going until I felt pretty confident that everything else was essentially 0. Even then, I'd probably still be a little shy. But Bogner's calculator will do this for me quickly. Let's see what Bogner's calculator gives me. So P of 4, and I want at least 3. My parameter is 4, and I want at least 3. There we go, 3, good. And you can see from the visual that it is including the at least 3 cases. Each of these pink, red bars contributes to this pink, red box. And so that's 76.19%. Make sure that matches the slides. Sure enough, it does. And if you don't like doing it with the greater than or equal to, you can also use the complement rule. And this is one of those situations where if I had to do it by hand, I would actually use the complement rule. I would find the probability of 0, 1, or 2. That's only 3 cases to test. And then subtract that from 1. And that should give me the same answer. Indeed, it does in this case. Okay. Any questions about that? Oh, I'm sorry. I forgot to show you this one. The probability the nest has at least 3 and no more than 6 eggs. So the probability that the number of eggs is between 3 and 6. The way to do that graphically, at least 3 is the 0.7619. I'll write that down for a second so I have it. And what I will do is I will find the probability that it's greater than or equal to 7, because those are the cases I want to throw out if I'm looking for 3 to 6. So for 7, the probability I get is 0.11067, and then what I know is the probability that it is between 3 and 6 is the probability that it's greater than or equal to 3 minus the probability is greater than or equal to 7. So 0.7619 minus the cases I want to get rid of. And let me just do that in the calculator because, again, I'm mistake prone today. .65123. Let's check and see if that lines up with what I expected here. So between 3 and 6, let's see, about 20%, 20%, 15%, that's 35, and 10%, 45%. Let's see. Did I do something wrong? 10, and 15 is 25. 40 is 65%. Boy, I just can't even add today. 65% is my estimate from adding those 4 bars together. That is correct. And on the slides, 65.123%. Excellent. All right. So just to recap quickly, we saw the definition of a random variable. We saw what a discrete random variable is. That's one that takes a finite list of values that we can list out. It doesn't have to be finite, but in this class we're going to stick with that situation. And for a discrete random variable, we can find from its individual probabilities, we can find an expected value and a variance. And it turns out the calculations are almost the same as the calculation of an average and a variance for a data set, for a sample. But we can use relative frequency or probability instead. Then we saw 2 specific kinds of discrete distributions. We saw the binomial distribution, which is where there are 2 outcomes and a fixed number of trials. So a binomial distribution has 2 parameters, the number of trials, n, and the success rate, p. From those 2 pieces, we can find the probability of any number of outcomes, we can find the expected value, and we can find the variance. Lastly, we looked at the Poisson distribution, which is another type of distribution. It counts how many times a particular event occurs in a certain fixed length of time. And all we need is the average number that would occur if we did this over and over and over again. From that, we can find the probability that any particular number occurs in that same length of time. We can also find the expected value and the variance. In fact, they both happen to be the same as that average in this particular instance. In all of these cases, at least in the binomial and the Poisson cases, I would strongly encourage you to use Wagner's calculators for those calculations. If you have a TI-83 or 84, they will do binomial distribution and Poisson distribution calculations. You need to do, I think it's second and I think it's 5 for the distribution menu. And inside of there, you'll find Poisson and binomial as options. It will do the same calculations for you. It doesn't quite do the visuals that this does, but again, if you have it on hand, it can be useful that way too. All right, so all that being said, are there any questions about what we covered today? Okay. If you do find questions come up, I have office hours Tuesday and Wednesday from 1 to 4.